message. The future is not set.
Camera and how they could have made it better. So this is going to be an approach a little bit red team, probably heavier red team, and a little bit blue team at the end. Can everyone hear me in back, just to be sure? Thank you. So we're going to edit things a little bit. Who am I? I am a retired engineer, just a retired hacker. Let's leave it at that. Just likes exploring. Even though I've retired, I still like poking at things and seeing what I can do. The motivations for this talk is I use cheap webcams for a locally hosted home security system. And by home security system, I mean I like to see the animals at my bird feeders. I am not really secure and the thing hiccups all the time, but I get cool video of deer and coyote and turkey and everything. Last summer when it got really hot, one of them started to die on me, so I did what anyone else would do. I went to Amazon and dropped $35 and got a new one. Swapped it out and put the old one on my workbench downstairs and left it until I was bored one day. It's like, what can I do with this thing? But seriously, a quick Shodan search shows that there are a lot of these things out and directly exposed to the internet. There have been, I was reading recently, there were some ransomware attacks where a camera like this was used as part of the attack chain because you're not running EDR or anything on a camera. So they launched the encryptor for the ransomware right from the camera. Yeah, these things are incredibly cheap, $35, and at that price point, I don't imagine there's any thought given to security. Okay, so one thing I do want to say is what I'm going to walk through is my normal approach to hardware hacking a device. It's not the end-all, be-all. There are better ways, there are worse ways. This is just my approach for what it's worth. I like to start, like I start with a software pen test with a little bit of passive recon. Now these cameras have Wi-Fi, and in the United States at least, you need to get FCC approval if you're going to transmit. And if you look on the label of the device, where the arrow is, there's a line for FCC ID and then there's some code number. You can drop that into Google and you're going to get the FCC report, which may or may not contain a lot of useful information. One thing I like to look at in these reports is there are photos of the thing disassembled when they took it apart for testing, and that kind of gives me some clues on how to take it apart without wrecking it. Also, there's user manuals. There's a spot on these reports for schematic, block diagram, functional diagram, things like that, but generally a vendor can say that's trade secret, don't publish it, and it's not published, which is too bad because it would give us a little bit of a leg up on these things. One thing I was really interested in with these cameras is how much do they phone home? I don't use any cloud-based thing for my home security system. As I say, it's hosted in my basement, but do these things phone home? So I took some time to plug this one into a managed switch, and I was port mirroring so I could see everything that went out. And you can see on this little bit of a Wireshark capture, it's going out to these IP addresses, and when I look them up, they're mostly servers on Alibaba. And what they're sending, and which is interesting because they're kind of black holed as far as DNS goes. They don't have any, they're not doing any DNS lookup at this point, so these IP addresses are hard-coded. Which, yeah, not too much fun. But what I did find, what it's doing is it's going out and it's pinging these Chinese servers, and it's sending the internal IP address, my external IP address, and the unique serial number of the camera. And this is used by the companion phone app. So there's a phone app you can get for people who don't like manually setting up their network stuff like I did when I set it up. So it can search your network and it can find these cameras and it can configure them all pretty seamlessly to a non-techie end user, which is handy. I just I'm not a fan of this stuff going out, but there really isn't too much that surprised me. Yeah, so you can see it's what that is. I ran Nmap on it, and the only TCP ports open were there's a web interface for managing it. There's RTSP because it's a camera, and the port 8080 is for the OnVIF server, which is another camera thing. There's also some UDP ports open, and I found, and they kind of cycle through as the things turned on. It's cycling through different UDP ports, and these are actually used by that companion phone app that I mentioned. And it's also, there's some capabilities for these things to peer-to-peer to each other that's built into the firmware. I don't see it happening at my house with the cameras. I'm not sure how you activate it. I don't know. These things are just what they are. I could have gone on from this point and started exploring the web interface. I could have started fuzzing the RTSP server. I could have done all of those things. But that really wasn't what I wanted to do with this thing. I wanted to play with the hardware. So I moved right on to disassembly. And again, those FCC documents help here because they show what it looks like taken apart. So I kind of had a clue as to what to expect when I opened it up. My family, my kids pick on me because when I'm doing things like this, I'm using the very least amount of force necessary. And they're like, just crack it open. But I like the possibility of putting it all back together at some point. There's a general rule that I've heard quite a few times that when you're hacking something hardware like this, get 3 of them. Get one for reference, one to rip apart and break, and one to hack. And every time I hear it, it's attributed to Bunny Wang. I'm not sure if it's his. Sounds like something he'd say, so I'm going to attribute it to him, just in case. So as I'm taking it apart, one thing I'm really particular about is I document this process. Every time I take out a few screws, I mean, we all have our cell phone right there, right? Take a few pictures, turn it around, take pictures from the other side. I'll make sketches of the connectors and the wires that go on them. And again, at some point you need to put this thing back together to make it operate. One thing I've been doing differently lately is fixturing. You can see later on this thing, I 3D printed a base to mount it on, to mount it securely. Because what happens, and what's happened to me in the past, is you've just got the circuit board, maybe you've got it held in your soldering third hand thing or something, you're trying to probe around on it, and the thing's moving around on your desk, and that's no good. Take the time, even if you just fabricate some cheap little fixture, you know, piece of wood with some nails in it to hold the board in place, you're gonna thank yourself later. The first thing I do after I get it apart is I start to identify and inventory components on the board. There's just a couple things I found. There's USB Wi-Fi, connectors. The system on a chip is a GOK GK7201 V200, and when I Google that, I don't get a lot of information. I'm sure it's an ARM at this point. I'm pretty confident it's an ARM. I'm pretty confident it's got silicon for image processing, things like that, but I don't really know much more. There is, right next to the SoC, there's an interesting little 4-pin unpopulated connector, which caught my eye right away. The other side of the board has the camera module, and it has a flash memory chip, SPI flash. So once I've, and again, documentation is key here. I have a paper notebook, and I'll start making a table, you know, what these are, and then I will, if I don't know what the components are, I'll Google or DigiKey, and to be honest, Google is getting kind of useless at this point with the responses you get. If you go right to DigiKey or Avnet or some other electronic supplier and start typing in the part numbers, you're going to get good responses, or good results sooner. And the nice thing about doing it right on DigiKey, for example, is you'll find a link to the data sheet if there is one. The system on a chip didn't pop up in DigiKey, so I never got a data sheet for that. From there, once I have the board apart, I start doing a little discovery with meter, scope, and some other things. First thing I always do is with the thing unpowered, I'll start checking pins to something that I know is ground. If we look back on here, there's an SD card slot. That's pretty likely going to be grounded, so I'll use that as a ground reference. Or I know the incoming power, I found that connector, I'll use that pin for ground. I'll start ringing things out, checking resistance to ground, looking for pins that are grounded. Then I'll plug it all in, and I'll carefully, now that I have good ground spots, is carefully start measuring voltages on these pins. I want to find out what voltage the microprocessor system on a chip is running, a microcontroller. This one ended up having several voltages. There's 3.3 volts, which was the I/O voltage. I'm pretty sure there was a 1.8 volt, which was either the, probably for RAM, or maybe that's just the core voltage. Just to get a clue as to know where to set things as I start poking a little more. One thing that I really want to find right away is JTAG, because if I have JTAG and the JTAG's enabled, then it's game over. I've got the whole thing in my control. There are products like a JTagulator or BlueTag. BlueTag's nice. It runs on a Raspberry Pi Pico chip. It's open source. It's a lot cheaper to put together than buying a JTagulator, and I believe the JTagulator isn't actually being made anymore. There's some support for it, but it's kind of end of life. BlueTag is nice because it will detect JTAG. It will also look for SWD if you have an ARM chip, which is something the JTagulator didn't do. Just another debug type interface. I struck out on this. I did not find any JTAG. If the JTAG pins from the SoC, the system on a chip, were brought out to a connector, then JTAG might be disabled because I just didn't hit it. The next thing I'll do is I have a cheapo scope meter thing. It's like one of these $100 Amazon things. It's good for 100 megahertz. It's fairly good. You can see the scope trace down there. I'll start hitting different pins, looking for signals, and I'm looking for something that's not a clock, something that's not just steady state. And as we see here, this trace I figured was a UART right away, just based on how it looks. There's more to this trace where when it's idle, the line's high. I can put some cursors on the blue lines, A and B lines, and measure the time of each pulse, and I can correlate that to a bit speed. I can do the math and figure out how many microseconds for 115 2K baud, or I can just look at this table I downloaded from the internet like 5 years ago, and it corresponded to 115K baud. So I'm pretty sure I got myself a UART. So my favorite tool for doing this stuff, people who do know me know that I'm just in love with the Bus Pirate. This thing does so much. I've had other Bus Pirates in the past. The Dangerous Prototypes, a company that makes this, has put out a newer one with the screen on it. You can see it on the left with all the winky lights on it. A lot easier to use, does so much more power. This thing's nice. And the mode that it's in here is a UART bridge. So it's basically just a TTL UART bridge back to my PC. So I powered it up, and I see this on the left. You see some stuff flying by. And the things that caught my eye right away is, wow, this is chatty. There's a lot of output on this UART. The first thing I see is that I'm getting output from U-boot. So U-boot is the bootloader. Nice, it tells me which version of U-boot even. It tells me a couple lines down from there, you can see in bold, if maybe you can read it, maybe you can't. Relocating the 0x43FCA000, that's interesting. I see some information on the SPI NOR, that's that flash chip that I found on the backside. I see that standard in, standard out, standard error is going to this UART, which is nice. And it does have Ethernet. I see this line that flies by real quick. Hit any key to stop auto boot. And it's counting down from 2, 1, 0, and then it goes on to auto boot. And what it's auto booting is Linux. This is running embedded Linux. The next line I see that is really useful is it tells me it's an ARM v7, which I guessed it was an ARM. And that's some interesting information to go on. So what I would do at this point is I would start exploring that UART interface. So you want to let me get over to, we don't need to see the display settings anymore. Let me get over to serial thing here. Okay, do you want to, Aaron's going to help me with powering on and powering off. And, you want to unplug it. So, Bus Pirate, I need to put it in UART mode. Sorry about that. First live fail. Won't be the only one, I'm sure. Okay, I need to turn on the power supply, and I need to put it in bridge mode. I'm just going to clear the screen here, so refresh. Okay. And then, yeah. So I'm going to stop it here real quick. So this is what we saw in the other thing. Please input U-boot password. I don't know the U-boot password. I tried some common things like root. I tried the model number of the camera. I tried the manufacturer. I tried a bunch of stuff. And I wasn't getting anything. I wasn't able to get in. One thing that I see here, though, is I can keep hitting this as much as I want. There's no limit on the number of tries I can make here. There's no back-off time. There's just wide open. So you see where the blue team stuff's going to go to eventually. The other interesting thing is it's in this mode forever until I power cycle. I can get this one. Power cycle it again. Let's let it go right ahead and start booting Linux. And as I said earlier, this thing is really chatty. There is a bunch of stuff coming out here. I'm going to give it just a second to go. It's going to get cranky because there's no network and it won't be able to do NTP. The camera software is starting up now. Just let it run a bit until it pauses for me here. Okay. So camera login, and this is Linux. I'm going to try the root user root. And nothing. Root, I can pound on this for a while. I don't know the password. It's not something common. It's not something easily guessed. So I'm stuck again. What am I going to do? So as I say, I can't get into U-boot. I can't get into Linux. So about that UART, looks like it exists as a development debugging tool. It's very chatty. There is so much information leakage here. I learned so much about the camera just looking at that debug output. But I need authentication for U-boot and Linux consoles. I can't figure it out. So I need to bypass this authentication. I'm going to focus on bypassing U-boot's authentication because it's going to be easier than Linux. U-boot is a single-threaded, bare metal binary, so there's a lot less going on. It's just the bootloader. And if I get the U-boot console, then I'm going to have a lot of control over this product. Insert evil F here, however you want to put it. How am I going to find the U-boot password or bypass it? My first idea was a side channel attack. This turned into a month-long side quest, as this says. So I do own a chip whisperer, and I could have used the chip whisperer on this, and I probably would have had success with the side channel attack. But one of the things I wanted to do with this is use cheaper, more available, more entry-level tools to attack this thing. But with the chip whisperer, I tried power glitching. The scope traces the power going into the thing. It's a nice, ugly bang. I tried EMP glitching. If you look in the top picture in the upper right, you can see a red thing. That is a chip shouter, which does a very precisely timed EMP pulse that I aimed at the chip. And I also tried some timing attacks. And the whole purpose of what I was trying to do with glitching is I see from when I enter the password that I can keep doing this over and over and over. I can use the Bus Pirate to trigger a glitch of some kind, whether it's a power glitch or the EMP pulse or anything else, because the Bus Pirate is sending the serial, right? So as soon as we hit the carriage return or enter, there's a short time, a very short time, is about 8 microseconds, where the camera was thinking about U-boot specifically was thinking about that password I entered to see if it was good or not. There's some kind of compare operation going on. It's a mem comp or stir comp, however you want to look at it. And if I can cause the system on chip to glitch at that particular moment, perhaps I can glitch right over that check and get into an authenticated state. It didn't work on the camera. The camera runs at 900 megahertz. My bus pirate, I can overclock to 200 megahertz. So it just didn't have the resolution to do it, the timing. What did come out of this, though, was some new firmware for the bus pirate that's pulled into the main build now to do this glitching attack. I had you can see in the lower right, there's a little circuit board attached to the bus pirate, so I made up a little hardware to do this. And at the end, it was a pretty useful thing for me. I learned a lot. The bus pirate has some new functionality that everyone can use, but I didn't get into the camera. So what do I do next? I'm going to get the source code out of the camera, and I'm going to attack it with Ghidra and find the password. U-boot is GPL2. I should be able to call the vendor and say, yo, I want the source code for U-boot with all of your modifications. Can you send it to me, please? This is an offshore vendor. I don't anticipate any kind of response from them for that. And honestly, it's no fun. I mean, let's get down to it. We're hackers, right? How much fun is it to write a nasty-sounding email? Send me the source code. So my next move was to hook a logic analyzer up to that chip. U-boot, as a bootloader, there's a very small section that runs right off the flash chip, and it's responsible. It's the first stage of U-boot. It's going to initialize the memory, initialize a few other things, and then it's going to copy the rest of U-boot's executable into RAM and jump to there and start running. I should be able to hook a logic analyzer up to the chip, read all of the stuff that goes onto the chip, or stuff between my system on chip and the flash chip, and I should be able to reconstruct the entire flash from that because the whole thing is being read out. My logic analyzer wasn't fast enough to catch it. The SPI is going on at 50 megahertz clock. My logic analyzer really peaks out around 24. So that wasn't successful. So yeah, let's just unsolder the chip and read the thing out. You know, it works. As you can see in the picture there, my flash chip is removed from the board. It's hooked up to the bus pirate. The bus pirate knows how to read most common memory flash chips, and it just read out the binary for me really neatly, and then put the chip back in. So what happened then is now I've got the binary. Let's look at it in Ghidra. Ghidra is a reverse engineering tool from our friends at the NSA. I think most of us know what Ghidra is. If you've used Ghidra on a Windows or a Linux or a Mac executable, it's quite a bit different from a raw binary. When you're looking at embedded devices with a raw binary that's running on, as we say, bare metal, there's no operating system, there's no external libraries, everything is self-contained in there, and you find pretty quickly that a lot of the nice things that you're used to in Ghidra don't exist. Right from the start, it's a raw binary. The Ghidra doesn't even know what kind of instruction set there is, so I have to tell it. And we saw this in the serial dump from that UART. It's a little endian ARM v7. So let's go ahead and give it a different name here. Give it a different name, we'll open it up. Trying to move along here. We'll do a quick analyze on it. So Ghidra is going to go through and try to disassemble the binary. And it looks like it's getting kind of successful. It's got the reset vector and the reset code. And again, remember with bare metal binaries, there's no operating system. Everything needs to be within this binary. In fact, if we look at the imports in Ghidra, there's nothing there. No, there's something there. Oh, external, because there are references to external memory that aren't included in here. Most likely libraries and things like that. In the interest of moving along, let's search for strings. And we know that the area of the code we're interested in says, please input U-boot password. So if I come here, I find please enter U-boot password, and if you were quick enough, you saw that there are no references in the code to that string. How does that work? So if you remember when I was describing stage 1, stage 2 of U-boot, stage 1 is just the bare minimum to get the chip configured so that U-boot can copy the rest of the binary into RAM to run faster than running off the flash chip. So we need to know where in RAM it put all that. Again, this chatty UART told us where it's putting it. If you recall in here in the bold, it says relocating to 4.3. So it's telling us right where it's doing it. There's so much information leakage. Sorry. There's so much information leakage in this thing. Wrong screen. So if we import the raw binary again, it's an ARM. Little Endian ARM, come on. Give it a different name. Now if we open it in the disassembler and analyze it again, so this is the same binary we just looked at. The only difference is no, I didn't tell it, did I? Gosh. Sorry, let me do this again. I skipped a step. Let's bring this in. We're going to tell it it's little Endian ARM v7. The difference this time is we'll go to options and we'll set the base address at hex 43FCA000 where it told us itself where it was relocating. Now, if it hadn't been as helpful to tell us that, there are ways to find where it's being moved into memory. It gets a little more complex, but it's definitely doable. Let's just get this thing opened up here. Open it up, analyze it. So you noticed it thinks it may have found the reset vector, but doesn't think it did. And again, it's because the whole thing is shifted up into this new area of memory, whereas this would have been running down at address 0. Now the rest of us is up at this other address. We're really interested in the password. I'm not going to spend a lot of time looking for other stuff. So let's search for a string that says password. Okay, what did I do wrong here? 43FCA000. Okay. Second fail of the demo. What I'm going to do is skip ahead a little bit also in the interest of time. Okay. I talked about U-boot U-boot or bootloader in general, or bare metal binary, not having any external functions, nothing loaded. So one thing that U-boot provides for developers is a function table that is used to provide the definition for functions like printf, getC, putstring, all of those. Because I have the source code for U-boot, the stuff they didn't modify, I can see the function table here I'm not going to take the time to explain how I found it in memory, but I found it and I labeled all of these functions with what they are to help me out, because then we can come to this function, which is the password entry function finally. So I changed variable names, I added comments, I did all of this stuff to make this more readable for myself and as an exercise. So this function is called in two places. It's called once where you hit the space bar to interrupt the boot process, and it's called again continually after that for every user entry in the console. The first thing we see is there's a global variable for console enabled. So we're just getting that from the global, putting it into a local. And we're saying if that variable is not 0, put out the string that says, please enter your password. We're zeroing out a local variable for position within the string. You'll see this in a minute. And then we enter a loop. As long as we're true, we'll do this forever. We're going to take user characters coming in on that serial UART. So that's where the getC is. User character. If that character happens to be a carriage return or an enter, we're going to break out of this loop. Otherwise, if it's a backspace, we're going to erase the last character that we entered. Pretty straightforward. And the backspace here is if our string is more, if you've entered at least one character, we're going to remove that one, decrement the position counter. Otherwise, we're going to put an asterisk on the UART, as we saw when I was playing around with it. And it's going to add it to a string. This buffer is a stack string that is 68 characters long. So as long as you keep entering characters, you're going to keep adding them onto here until we've hit the return. We come down here, we null terminate the string, we put out a carriage return on the UART just to be nice, and then it does a string comp of what you entered to this string. This string, if we look it up, constant char, is simply HI2105 chip. There's our password. I'm going to talk about this function again in a little bit, but I just want to skip that for now. Let's go back to, so we've got the U-boot password. Now what? We're going to play around a little bit with U-boot. I'm just going to jump right to my serial console again. Can you, hit me again, please. Yep. Okay, so I interrupted it. Now I'm going to enter HI2105 chip, and we're in. Hacker voice, we're in. So if I look, this is a U-boot. Yep, we're here. U-boot does a lot of things with environment variables. That's how it controls the booting process. So the arguments that get passed to the Linux kernel are right here. I want to change these. This is the whole purpose why I wanted to get this console. So I'm going to set environment, boot args, and I'm going to copy this stuff. I can't copy around the end of line with this terminal emulator. So I'm just going to do this. Paste. It ends in 9.2. And then I'm going to add init equals bin shell. When the Linux kernel loads and starts running, it's going to start the init process. The init process does everything Linux does when it starts. I'm just going to, because I'm doing this live and I probably screwed it up, I'm just going to print the environment again and make sure that I see it. Okay, so the boot command. Okay, so we'll paste that in. We'll start. It's going to boot Linux, and boom, it's done already. We are root. Yeah. But thank you. But I want to persist this because the init process didn't run. So all of the camera software didn't run, so I'm not really getting where I want to get yet. So let's take a look in the etc directory, and we're going to take a look at the password file. This is disturbing. There is only one user. That user is root. If you were to get remote code execution on this camera, you don't have to bother doing any privilege escalation because you're already there. If you're not familiar with the format of the Linux password file, the first, it's separated by colons. The first is the username, the second is the password. Then we have user ID, group ID, group name, home directory, and interactive shell. There's an X in the password. That doesn't mean the password's X. That means the password is in the shadow file, and it's this. It's a hash, right? Good news, bad news. It's a hash. We knew that. It starts with $1. This is an MD5 hash. My notebook here can plow through the whole of RockU text with an MD5 hash in about an hour, and there's no GPU on this thing. It's not a very secure hash. I did do that. I didn't get the password. So I don't know what they're using for the password. I don't care. What I'm going to do, because the root directory is in read write here, I'm just going to copy this, add me as a user, and at this point, a lot of tutorials and stuff would tell you, okay, now go to OpenSSH and run it with the password command and create a hash for a password you know and then enter it into the shadow file. Yeah, you don't need to do that. I'm just going to leave that field blank. I'm just syncing it because I don't want to mess up the file system. I'm going to restart it. Now that environment change we made just a little while ago to be able to boot into shell instead of running the init process, that was just in RAM. So the next time it boots, you can see it's starting up all the camera software. Yeah, give it just a little bit. Oh, come on, we're running out of time. Okay, so camera login. Come on, hurry up, get through. Okay. Okay, well, and here we are. We are back here, no password, and we are root. So the camera software is running now. I plan to explore that a little bit and talk about what's going on with the camera, but let's just shortcut it to say there's one process that's doing all of the networking. I did Ghidra that a bit, and I found some vulnerabilities. There's some problems with this thing. Let's leave it there. So we went to the UART, and again, Drake meme, cracking root's password hash. No, we're just going to add that to etc password since we had write access to etc. Okay, let's talk about what the vendor did well. Root's password was not easily cracked. Okay, I don't know if they just picked random stuff or what, but it's okay. The U-boot console is password protected, just not very well. I found that the embedded Linux build was pretty well done, actually. They only had what was required. It's a relatively recent kernel for an embedded device. BusyBox only had what it needed to have for commands. There are no extra libraries on this thing. They did leave behind some clues to me that they're using a union mount or an overlay file system for development or debug. And if you're familiar with that with Linux, basically what I'm guessing is they stick an SD card into that SD slot, which contains many other commands that are actually useful for doing things. And that file system gets overlaid onto the root file system. It's a nice way to do embedded Linux development. What could they have done to make it more secure? They could have picked a chip that had some security features like key storage and things like that. Could have picked a flash chip with no lead footprint. Laser or other ablation of markings on the components would have slowed me down. An opaque conformal coating would have slowed me down. All of this costs money. They don't want to spend money. This is not an exhaustive list. Firmware could have done some threat modeling. They could have implemented secure boot if they had the hardware. They could have signed the file system. They could have encrypted the file system. They could have encrypted the second stage of U-boot. There are a lot of things they could have done. One great big thing is they shouldn't run everything as root. We know this principle of least privilege. That function that we disassembled in Ghidra, talk about that real quick. Secure code reviews would have been nice. He would have caught some things. Limit password attempts, add some rate limiting. Store the hash of the password and not the actual password to memcomp by. So when you enter the password, it hashes it, compares it to the hash thing. And added some variable stuff. So that stack buffer overflow, I don't know if anyone was looking at that while I was going through and saying, dude, why don't you just use that buffer overflow and you don't need to mess with any of it? A couple problems with that. One, return-oriented programming, there's not a lot to work with a bare metal binary. I could have probably found something, I might not have. There's no library functions to pull in. And the key, the real reason I didn't even look at it, is if you think about this function, we don't return from this function until the correct password has been entered. If you're writing a stack-based buffer overflow, one of the first things you're doing is you're replacing the return address with one that you control to jump to code that you either control or that you want to for return-oriented program. We don't return from this function until you've entered the password. There's no point trying to do a buffer overflow because if I could enter the password, I don't need any other code execution. The next group is coming in. They're antsy. So I'm going to wrap it up with that. Any quick questions? All right. Thank you for your patience. I appreciate the patience with the delay. Thank you to the hardware guys. Thank you very much for getting that worked out. And enjoy CypherCon.